are live. Mm. Mm. Okay, so let's start. Mm. Okay, so guys, so so today we will be studying lang chain from the starting. Not a lang chain, maybe we'll be learning lang graph. So I think LangChain as a concept is kind of a very interesting. So it can help us to build LLM models, products around LLM models. So it's kind of a very great framework created. It's very vastly being used. It's so vastly used, like companies like OpenAI, Anthropic, they contribute their particular packages into that, right? So so you don't have to import the OpenAI SDK or something else. And let's say one day you are working on an OpenAI model and you want another model for Anthropic, so you don't have to do anything else. You just have to import that mod package, just that only. So we will come to LangChain. Actually, I was trying to learn the LangGraph for one of my projects, and I think this is a very good thing to do. This is my first streaming, and I was thinking, why not do it on live? Why don't we learn this thing with the all of you people? And that's why I'm here. Okay, guys. So uh, let me let me give me 1 minute as well. Let me set up something, as this is my first time doing this kind of a thing. So it is good. Uh, Now I can see the stream is going healthy. This I can see the stream key and everything, and I enable auto start or something like that. So I am using Restream. This first time I'm using. Next time maybe using something else, maybe some OBS or something. But right now I'm using this. So let's deep down into it. Okay, okay. So I'm using LangChain Academy for this particular thing. Okay. So what is the LangChain, right? So LangChain as a concept is very interesting. It's created by a bunch of people. They wanted to implement something great. So they created some interesting course. I was looking into that. So before that, I was learning using deep learning.ai, LangChain, and I was learning using Databricks LangChain. So I came across the LangGraph, and it is very cool thing that I saw that they have their own course made by themselves only. So I'm really interested in what they have built, right? So this is the one, and I will attach the link as well for this there. So introduction to LangGraph. So LangGraph, we will learn about what is a LangGraph, what is why it is different from LangChain and everything. So it's a basic building agentic multi-agent application separate from LangChain being a LangGraph has to control developers add better precision control into agentic framework. So yeah, so we will be learning something like that: introduction, state and memory, UX, human and loop, building assistant deployment, FAQ, what is a LangGraph platform. So we will come to that. So this is not very interesting for us. So what we will do, I was going through this course, so as I clearly explained, right? So let's get to it. What we are doing. So yeah, let's listen for this. Okay, okay. So one thing he interestingly said that, right, in a chain, what we do, we pass the control from one chain to another, right? Now he said very interesting. Now there's something on LangChain already present, but they develop LangGraph as well. So what they are doing, they are providing more control to developers to have a to create a more intelligent, more controlled, right, more robust kind of agentic AIs with the help of LangGraph. Mhm. Okay, okay. So let's listen again. Right? Now he clearly explains why he's built that. Okay, 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 Okay. Okay. So right now they are giving introduction. So let's move on. Uh, I generally, what I do is, so these courses are generally created on one XP, right? So most of the thing is this and that, giving introduction and everything. Right? It's a very introductory course. So whenever the course is created, they keep in mind, okay, every kind of person can be catered. Because we as a developer, we know what we are going to learn, right? So I generally skip to 1.5. Okay, so I think this is what that they have set. Let's see what is the getting set up. So welcome to Langchain Academy. Introduction to LangGraph course. This course is divided into six modules. Okay, that we know. In each module, students have directly each module is set up. So they have recommended something for us, right? Ki what, what, what is what, and what we are going to do. So they have given us something set up locally or something like that. So what I'm going to do, I'm not going to use it locally, right? Probably be using going through that because the thing that I want to do, I want to go to theoretical first. Matlab, my funda is kind of a that I wanted to understand what is going on little bit because the theory wise that the LLM and LLM chain, right? So I know what is LLM chain, but I don't know their basic terminology on that sense. Like what is their state, what is the node, what is the edge. So we will come to that part. So I wanted to go that. I wanted to observe what is something like that, and we will eventually build up from beginner to intermediate to expert. I don't want to jump my horses into the expert part. Okay, so running notable, LangChain, Tracing Key, OpenAI, and Gravely API. Okay, see, I think that is cool. Like, I think we can continue. Right? Okay, so I think what they, I don't want to go into over that. Right? As I told you, I'm not going to use zero. So I'm going to do introduction. So let's see first introduction. Hmm. So so they are very different kinds of architectures, right? If we are going to see, let's say, different kinds of agentic architectures, like not these ones, like React. Okay, I will give that document. I think so. React is coming some kind of a processing that we do. We talk in some particular way, like thought processing and everything. We provide to LLM how to thought, how to think about that problem. So this is something like that. What he was adding. Okay, okay. Let's dive into model one. So Langchain introduction, motivation. Okay, let's go to this PDF what they have given us. LangChain Academy introduction language. So in a solitary language model is a fairly limited. Okay, so generally what we do, let's say you import OpenAI, is right? What do we do? We have LLM model, you import model, right? You query that, you put in a message there, and you get a result. So this is something like that. Start LLM. And example, accelerates, multi workflows. Yeah, so you can add tools and everything. So many applications. So now, so many application LLM application use control flow. Let's say step one, they do LLM, then step two, step three, step three. With each step, pre and post LLM call tools call and interpret. So it's kind of a conversation that you in ChatGPT, right? You have like if let's say I'm supposing whoever is watching it's kind of a developer only. Let's say they provide system prompt, okay, then you put it into the ad key, okay, key what is system from, and then what user put a query. User put a query, then according to that, assistant answer that, right? User assistant. This is kind of a conversation that so what they're saying, each step is like that only. Each step is like that only. You are having conversation, and each step is each node is there is a conversation. So this is a control flow. We can, if you want, we can check that only, and this is comes in all the lag from scale like retrieval, ret- retrieval augmentation. That way. So control flow form a chain like so. Nothing but a lang chain concept only that they are trying to tell you. Chains are reliable, same control flow every time. So what chain provider? Lang chain has a very good thing. Like in a very traditional system like uh, we are using OpenAI SDK, right? You don't have a particular format created on that part. So what you want key, you have to have something key. Every time when I put a X, I want a Y, right? At the end of my journey. So how we make ensure that we can break down the problem in smaller parts and put a breakpoint. Yeah, okay, you have to do this, you have to do this, you have to do this, and yeah, it will get. Now, what we would let's say we had a big query and you say, okay, okay, process that. So LLM is nothing but the information retrieval kind of a system. So sometimes it will pick that, sometimes it will pick that, right? So you not necessarily every time the kind of a result that you want, you will may not get, right? Very good amount of time. So what are you saying? Ki chains are reliable. When you break down a chains are reliable, right? But we want LLM system that can pick their own control code. Okay, so now lang chains have that very singular thing. Okay, you have to follow this. Now, what we want the LLM to have to pick their own control flow. Let's say they only choose what step needs to be taken. Let's say from step one they want to go step three or step four or step five or step six. Right? It's kind of a tree traversal only. They want to tree traverse. Okay, I want to be there. I want to go there. I want to go there. Okay, I don't. I want to stop there. Something like that. It's something like that to have a control. Agent is not equals to control flow defined by LLM. Okay, I don't understand that part, whether they are saying not equals to or equals to. But what I understand from here is like it can choose two or three. Fixed versus LLM defined flow. So here we seeing this is a fixed. This is LLM defined. LLM defines which steps to follow. Okay. So this is what I'm an agent, right? Agent is nothing but who can decide from itself. Okay, I will choose this path based on some feedback or something, some result. Right? So kind of agents that we have. Let me little bit zoom here. Okay, kind of agents. So router. So router is nothing but a kind of a chain in LM chain, right? So we have a less control over there because LLM decides. Remember, LLM only decides key which step it needs to go. Now in a fully autonomous system, like I'm not sure why they are saying fully autonomous. Let's say they are saying they have a full control over that. So maybe they are going to explain, okay, something new. Let's say full autonomous system they want to build. They have a full control there. Let's open this. What's NG? For instance, if it comes a wide range of work, I can think of one example where someone deployed what they called a machine learning algorithm. A senior member of community is saying that that's not a machine learning. Indeed, a linear regression using a least square cost function has been mathematically legend and Gauss in early training long before invention of computer. Yet machine learning was embraced these algorithms. We routinely call them a machine learning introductory course. In contrast, about 20 years, I saw statistical department at a number of university look at a development in machine learning, say that's not a really statistics. And that is the one reason why machine learning grew much more in a computer science than a statistics department. Okay, so what he was trying to tell you, okay, people in the statistics department generally don't think that whatever the background of the deep learning and LLM development is that's not a statistics, real statistics. Okay, this is one my machine learning group. Furthermore, since then that most statistical department have become much more open to machine learning. Yeah, malab, I have seen that recently. Uh, Great deep learning engineers are really good at stats. Really good. Means they have a tremendous mathematical capabilities and statistical algebra. So this contrast came to me a few months ago as I thought about how to talk about agentic system that use a design pattern such as reflection, tool use, planning, multi-agent collaboration to produce better result with zero short prompting. Zero short prompting, nothing but without any given example. So this is nothing but that. Right? Planning is nothing but you plan something out. Okay, okay, I have to do this, that, and tools is nothing but that tools you use. Like generally, in like in MCP that we have seen like different kind of apps being added right based on the API calls they communicate. I had been involved in a conversation about whether the content system should count as agents rather than having to choose whether or not something is an agent is a binary way. I thought it would be more useful to think system as being agent like different degrees. Unlike the noun agent, the adjective agentic, okay, allow us to contemplate the system include all of its in this. More and more people are building systems that a large language model multiple times using agentic design patterns, but there is a gray zone. What clearly is not an agent, prompt-based model once. So what he's trying to say, there is a notion going on, like so prompt-based model is not an agentic. And what clearly is an autonomous agent that gives a high-level instruction plans, uses tools, carries out multiple iterative steps of processing. Okay, rather than over which work to include or exclude as being a true agent, we can acknowledge that there are different degrees to which system can be agentic. Okay, so he's trying to draw parallels between what is a statistical, there's a statistical department and a CS department, right? And machine learning department, and what is agentic and what is the agent, right? So something kind of like that. Rather than arguing over which work to include or exclude being a true agent, we can acknowledge that there are different degrees to which system can be agentic. Then we can more easily include everyone who wants to work in agentic system. We can also encourage newcomers to start building a simple agentic workflow, iterative making system more sophisticated. In the past few weeks, I have noticed that while technical people and non-technical people like sometimes use the word agent, mainly only a technical people use the word agentic for now. Okay. So now I see an article that talk about agentic workflow. I'm more likely to read it since it's likely to be it's less likely to be asked. So we I think I can relate to that part. So being in industry, so people generally use agent, non-technical people, because they don't understand what is different between agent and agentic. More likely to read it since it's like to be marketing fluff and more likely to be yeah. So I think he wants to highlight on that part only. So I think what he did, he put his thought, whatever he was going through, like after open chat GPT went boom and everything, the when every industry wants it to implement AI. So that is a very cool thing to do. But even the simple thing like that can be done using Python scripts, that can be done. So very small automation. They wanted to include AI just for a namesake that they want. They have made the agentic something in their work, right? In work day to day life. So yeah, so I can understand like more on a corporate level in a large number of industries. I've seen that more people are going into the marketing bluff, like wanted to implement AI. And there's another side to that, that people wanted to do the in baby steps because no one knows how to implement these kind of a things particularly, but eventually they wanted to build up. So they are going very small steps. Okay, building a solution which can be done with other system, let's build that with the AI. Can we build up to the more sophisticated solution that he wants it to say? So maybe that is a one thing, right? So okay, okay, then let's back to it. Okay, what is a cognitive architecture? Let's not go there, but let's see once. What's the harm? The term cognitive has a rich history in neuroscience and computation cognition per Wikipedia. Mm, mapping of level of autonomy. So what he is saying, there is some, they have published on blog. Levels of autonomy in LLM application. Human driven code, LLM calls chain router. So what they have done, they have built some kind of key lines keep when it's LLM written, when it's the code, right? A human driven code decided to step out of a step, decide when step to take. I think code, yeah, I can understand that. LLM calls one step only. Chain multi steps, yeah, decide to step out of it. What steps to take? Router, yeah, router you can add key when step, which step when to take. And it's little bit close to line graph, so it's kind of a middle in between line chain and router. So agent executed are nothing but decide output of step. So agent decide one output of step. So what he has given ki what is a human driven and what is a agent execution driven. So it's a good paper. I have not read it, but am keen to learn. I want to go through. I'm putting it back right now. Oh, okay. So let's see. But practical challenges. Okay. So what they have done, they have simplified. Don't go to read that. Here what we have simplified. Less control, more control. Code. So now code, what they have this code, we have reliability, high reliability, but agency or flexibility. So code is very static kind of a thing. So let's say you have written a code x equals to 5. So it will be x equals to 5. But if you put x equals to random, now it's a very its reliability goes down, but agency and flexibility goes up because it's flexible to take any amount of value that you have given the range. So it's very flexible, but other time you lose the control because you exactly don't know what is going to be printed. You definitely won't tell, you can just possibly guess. So that is something very simple example that they wanted to say that the code we have a large, they have a high reliability but a low latency because that can be very flexible. So then it came to LLM calls or LLM chains, they have a little bit of more agency of fluency. So agency, not agent in something like, so they have given some adjective kind of a thing. So flexibility, they have more flexibility and less, little less reliability because LLM, that is hallucination and everything. Yeah. So then comes the router. So router is a middle kind of a thing, right? So think about chain. Let's say there is a chain going on, and you put a router there. Let's say if you have built, if you have done the ETL diagrams and everything, you have seen ki, okay, we put a if else in a diamond box, right? So it's kind of a diamond box you put there. Ki, okay, if the output from this is that, yes, so go to this chain. If it is no, it go to that chain. So this is something like that. And now that comes a fully autonomous. So what is a fully autonomous? Okay, so let's say we have a very uh, we have built some kind of a system which is very, you put it there and it does some kind of wonder, right? So now we are not sure how reliable it's going to be, because we exactly don't know what is how it's going to work, because we cannot explain it now. But its agency and flexibility is so much large because it can do a number of things. But what I ask and what I will do, it's very different kind of things, right? So then Langgraph helps you to reliability curve. So what is Langgraph do is it push the curve. So what Langgraph provide is it's a next way of doing things, right? So you have a routers, you have after a router, what they thought, okay, let's build something more control based, but which has a more reliability and more agency. So Langgraph provides that kind of a control. Okay, ठीक है. Intuition let developer sets apart a control flow reliable. Let's say there is a step one and then step two. Then we inject the LLM to make it agent, right? So to make so there is a let's say you have a system, right? And in that system you have like step one, step two, right? And that is a very reliable code. And you wanted to make more flexible. So what you did, you add LLM. Okay, let's say you let's take a very basic example, and user enters a two number, and you want to do addition. So what you will do, input two numbers, perform operation, give output. So there's a three-step solution. Now what I told you, ki, instead of some of in step two, I will put that agent LLM. I put not agent. Let's forget about that. In the words of Andrew Andy, let's not use agent. Let's use LLM. Right? Let's. So what LLM does is you input a two numbers X and Y. You can do any number of mathematical operation on those two numbers with the help of LLM, and you get the output. Now in the first workflow, what we did, what we learned is that key there is a more control but less flexible. But with the LLM, what we introduce, it gives us it reduces our reliability because we don't know what is going to be performed on it. Let's say we say ki, do some unique kind of a mathematical operation, but it can, but will it be able to perform based on its capability or not? We are not sure, but it can. But if it is correct, it can perform wonders. So it provides more flexibility in the solution. So LangGraph Express custom control for is graph. So what they have done something kind of graph based system or something like that. So where node one goes to LLM, right? And if something is wrong, it goes to node one again, and it follows the something and over. So it gives the control. Memory shared across the graph. Node tools nodes can tell tools and modify state. Planning edges can control flow based on LLM decision. Okay. So module foundation is LLM foundation chain routers. So we will be learning about that. We will come to that part only. Let's back to the course. Okay. So this is something like that. What they have built is so there is a lang chain. Now what this they have built very tremendous thing. Then they have pushed their boundary and created a lang graph, which is more reliable, more control given driven, right? And they have something called industry driven langsmith. So it is a very so every open source industry, what it does, let's say Airflow is Astronomer is present, for Spark it's Databricks present. So these kind of so when they build a Lang chain, it create a commercial application called Langsmith, and we will cover that as well. So Langsmith provides us the feedback. It it shows us how many tokens are used, how agents are being communicated, right? So it helps us to debug, use the playground, prompt management, annotation, testing, monitoring, right? So in industry, you need these kind of a tools, right? Whenever you're using because uh, the data is very sensitive, right? And the output that you give, it's going to the end user who's paying for your service, right? So these kind of things will need require, right? In every kind of a system, and basically like LLM is such a hallucinator, right? So we need this kind of a system in our in some in commercial projects, right? Or that is a land graph platform, right? So, LangGraph platform is nothing but an integration of LangChain and LangGraph. So LangGraph platform covers everything. So yeah, this is that, like lesson two, simple graph notebook reference for simple graph UI only. Okay. Um, Actually, we can do two things. Let it open, and let's open another tab for module one resources. Okay, let's deep it and deep down in the. Just give me 1 minute. Uh, let's go to video as well. By that time. Okay, so what we went to say, they are explaining it here only. Keep what is what and everything. So let's listen. Let's go to it very briefly and let's continue that part. Okay. Okay. Yeah. So and in the words of Andrew NG, right? To make system very agentic and not in the words of NG. So so it based on the context, right? For that, step one, step two, step three was a agent, but today can we have a capability to LLM to decide what step to follow and everything, right? So yeah. Okay, so what they control, that what they're showing is this LLM control, no, not the human control. So I misinterpreted. So this is that kind of that X framework that I show you, that X graph. So they are represented in kind of a this, and there's a theory of networks, right? There's a very interesting book uh, by Tanmay Chakraborty from IIT Delhi. So I've taken his course while in masters. So in every natural occurrence of network, right? Any kind of a network, any kind of what you see, you always see this kind of a graph. That that this is very fascinating. Like like a Gaussian distribution, you have like this kind of a thing, right? Inverted U, something kind of thing. You have this kind of thing. Just read the theory of networks. You will see that is a very interesting. That's why I love. That's where I fall in love with the networks and ML and everything, right? And that's why I'm more interested in learning the language. So what? So what he is trying to tell is the LangChain and LangGraph are the same thing only, but there's an extension. So what they have done, there's a marketing gimmick to build up something over that. So nothing else. Yeah, so he's drawing parallels between a LLM router, LM chain. We have a router chain, right? And they have a generating tool called assistant, right? So something that they are trying to show you what is the language graph. So what is new? Why they have built a language graph? So let's go to that. Oh, nice. Okay, let's go into the code. Yeah, why not? Oh, okay. Let's go to simple graph. What? Okay, so what they're saying. Okay, let's listen. Then I will try to explain to you in little bit of uncluttered words. So before that, right, everything going to into that part, there's something I wanted to learn about. Let me see where it was. Okay. Okay, so let me go there. Overview, line chain, okay. I wanted to learn something about graph right first. So what they have done, they have gone through, but I wanted to learn deep down. I want to know what I'm implementing, what is it internally doing. I can build. I see we can go into chat GPT and build these kind of stuffs, but I'm really not that kind of a person, and I will not be doing that certainly. And so that's why. Hmm, okay, let me do one thing. Okay, let's about graph. So at its core, line graph models agent workflows as graph. You define the behavior of agents using three components. So Lang graph models agent workflows as graphs. So what in Lang graph agent works as a graph. Mm, okay, so they have a three main components: state, nodes, and edges. Okay, I know nodes and edges are something, but what is a state? A shared data structure that represents the current snapshot of your application. Okay, so okay, it can be Python data type that it typically stores a typedict or pydantic base model. So what I understood is that at what stage my current application is on. My thinking is that it stores your data. What all things have been going on. So in every node there is some kind of data structure. It stores what it generally it is stored. It is on. Let's say there are two nodes, right? You started on, let's say, assistant user, right? And the next node you go, they're all force, but there are a couple of conversation as well. So so this node shows you have a have two conversations. This shows you have a three conversations. So there is a state maintained. So what I'm thinking is that the state stores what in that particular node, what is your conversation history, or what where your model stands, right? Yeah, I think that is the one thing. Nodes. So let's see what are nodes. Python function that includes the logic of your agents. This receives the current state as an input, performs some computation on or side effect, returns state updated. So I think this is kind of a wrapper. So in the Python function your state resides. That's what I am thinking, right? Key. So you need to store your state, right? And to store your state, let's say, you have to have something where you can represent that logic. And what better way is to have a function. So I think what a nodes are nothing but a kind of function which wraps your state. Okay, now Python function. Okay, by the way, I have something called this only. So let me add here. State is nothing but what is your current application has. Let's see. I don't want. Okay, let me put it there. Some kind of. Let's say we have two nodes, right? In node one, I have like assistant human, human. This conversation I have, and node number two, I have like this only, but I have extra conversation. So now we have a two states present, right? It's nothing but like a doing commit on a different nodes. So before that you have this node, now you have this node. Let's say you want to You move to, let's, there is a chain called which moves from 1 to 2 and 2 to 1 if something bad happens, right? So when you move to 2 to 1, you are losing your you are moving to your previous state. In that way, you are not losing anything, right? You are not subtracting from yours, but you're moving to your previous, right? And think in a very large scale, right? So that is help us to, it's nothing like a commit rollback, right? So this is something very very good, right? I really like that. So yeah, like nodes are nothing but like, let's we discuss, is nothing like a wrappers which wraps the state. Yeah, that I understood from that, right? And this Python function that determine which node to execute in next based on a current state. So yeah, so state defines where it needs to go, right? They can be conditional answers. Yeah, yeah. So I think that is very clearly understood, right? By composing nodes and edges, you can create a complex looping workflow that evolves. Okay. You can create a complex looping graph and evolve state over a time. The real power through comes from LLM graphs, manages the state. I have to read it again. By composing nodes and edges, you can create a complex looping workflow that evolves state over time. Okay. So whenever your chain is moving, like in your moving on control with the control looping, you evolve over the state over time. So your state variable is evolving. The real power comes through from Lang graph that manages that state to emphasize. Okay, so yeah, that is very clearly understood. So everything is like a tool for it, but state is a very important thing. Lang chain handling the state is a very important thing. Yeah, that is right. Actually, right. Now let's move to emphasize nodes and edges are nothing but a Python function. Yeah, that we clearly understood, and they can contain an LLM or just good old Python code. Yeah, yeah, that is right. Matlab, if even if you don't have a Python function, you can create a graph, right? But that logic, that state thing, right? Um, it can be replaced with a Python function to, because we are not we are sending something and we are asking where to go from there, right? Something like that. In short, nodes do work. I just tell what to do next. Yeah, matlab, they are saying something like that, but in node states do tell ki what is going to do, and edges tell us you have these kind of a paths. Where do you want to go next based on your state? Simple. Line graph's underlying graph algorithm uses message passing. Okay, what is message passing? Okay, message passing to define a general. So message passing nothing but passing from one state to another state. So this is a very simple CS concept. Message passing to define general program. When a node completes its operation, it sends data along one or more edges to other. The recipient nodes then execute their function and pass the resulting message to next of set of nodes. Okay, when a node completes its operation, it sends message along one or more edges to node. ठीक है, एक node खत्म होता है तो then we will able to understand कि it's going to one or more edges. Sorry, I'm my Hindi just spoke up. I try to understand, so in mother tongue only I can understand some things. These recipients nodes then execute uh, their functions and pass the resulting message to the next set of nodes, and process continues inspired by Google's Praggle system. I think they have inspired from Google Praggle system. We will see. We are more interested in line graph only. Message to the next set of, okay, so in the recipient's node where the control has been flowed, like one or more nodes from that particular node via edges adjacent to that, uh, the resulting message to the set of node, the process continues, right? So it's nothing but you're traversing a graph, kind of like in a BFS or a DFS, maybe we're flowing control from one part to another. The super stack can be achieved considering a single iteration over a graph node. Nodes that run in a parallel. So first of all, I want to tell you this is a graph, not a direct acyclic graph. There are loops in the Lang graphs because that makes this uh, agentic, right? So having a human into the loop is a very important thing. For me, at least for me, it's something like that. To have something like in Chat GPT, if you're thinking something like you have a conversation, you bring into the human. So which I understood that having something like that makes system very trustworthy. Can use it with a single iteration over graph nodes. Nodes that run in parallel are part of a super step. Okay, while nodes that run sequentially belong to a super steps. At start the graph execution, all nodes begin in an inactive state. A node becomes active when it receives a new message. The new message is nothing but it receives some state on any its become or channels. Active nodes then runs its function and responds with updates. At the end of each super step, nodes with no incoming messages vote to halt by marking themselves inactive. So let's say you move into the chain where there is no coming back. So they just say, "Ki, okay, we are halting. We are going by. Bye bye." No message to come to hold, marking themselves as inactive. The graph execution terminates, all the nodes are inactive and no messages are in transit. Yeah, I think that is kind of optimization. Yeah. State graph. The state graph class is a main class to use. This is parameterized by user defined state object. Okay, so there's a so it's oops. Compiling your graph. To build your graph, you first define the state. Okay, and you then add nodes and edges, and then you compile it and what exactly is coming graph and why it is needed. Okay, so first thing you have to understand, you have to declare your state, then your nodes, then your edges, right? So that's make the graph. You have to understand ki what is your state is going to hold, that you have to know the beforehand, right? After that you have to know ki what all nodes that you are going to get, right? And what's the relationship. So these two things will go simultaneously, right? What state, so state is nothing but a problem. Let's say I wanted to pass on the messages. So message. See, I have a problem. Let's say I wanted to build a chatbot. Now I know ki from one, let's say in where it calls some other agent and it calls some other tool, right? Let's say some kind of a simple architecture. And so then I know I'm going to pass on messages, and from the tool I got some messages, right? In some kind of a text I will be getting in some definite format. But I also know I will be needing, already needing 2 3 edges, and to connect them I need nodes, and to connect them I need edges. So all things are going simultaneously, but then I draw them when I go like, okay, these kind of a flow, this is what kind of a flow that I would be needing. Okay, to build your graph you first define your state. There's what exactly compiling your graph and why it is needed. Compiling is nothing but we will see. Compiling is pretty simple stuff. It provides few basic checks on structure of your graph. No orphan node. Let's say you created a graph, there's an orphan node is present. Means there's no connectivity. That what's the use of that part here? It is also where you can specify runtime arguments like check pointers, break pointers. You compile your graph. You call the dot compile method. Yeah, so we will come to that part as well. You must compile your graph before you. It's quite understood. State. The first thing you do when you define your graph is define the state of the graph. The state consists of a schema of the graph. Okay, schema of the graph as well as the reducer function. We will come to that as well, and which specify how to apply updates to each state. Okay, so what reducer function does is it helps us to apply the updates of the state and state as a variable stores the schema of the graph, and state is wrapped to state graph class. Okay, I'm getting some hierarchy graphs there in my mind. The schema of the state will be input schema to all the nodes. Okay, that's quite understood because state is state. Okay, and edges in the graph and edges in the graph. Okay, yeah, quite understood. It can be either type dict or pydantic model. Okay, I don't know what is a pydantic, but we'll come to know. All nodes will emit state updates to state which are applied to a specific reducer function. Okay. So what I understood from that is key that state will be an input to nodes and edges. That is quite understood because in edge you have to know what is the input that is coming. Let's say I have a router. I on yes I want to go there. On no I want to go there. So edge has to understand that what is coming from. So what is coming from what, right? And we know nodes are nothing but a state right now in lang graph. So state in from the state the input is coming to the edge, so it able to understand the lang variable, the state variable. Same goes for nodes as well. Actually, now we know which edge to active. Now that output will go to nodes as well, so it has to understand the node as well. So state has to communicate state as well, state has to communicate edge as well. Yeah. Yep. Schema main document way to specify the schema of the graph is be using a PyDict. Okay. Mm, I can understand it. The main document way to specify schema of the graph is using type dictionary. If you want to provide default values in your state, use a data class. Okay, specify schema for graph is by using type dict. Hmm. If you want to provide default values in your state, use a data class. Okay. Okay, so we can define the schema actually with the help of type dictionary. So there are two kind of a things. It can be PyDict or the and PyDicting models. Okay, the schema of the state, and with the help of that, we can provide it. What I click type dictionary. Okay, so it converts everything into dictionary. Okay, okay. This one way to do things. By default, the graphs will have a same input and output schemas. Okay, I don't understand. We have only one graph. Graph will have a same input and output schema. Okay, so to understand that there's a start node, there's an end node. The schema of the input from the start node is same as the output from the end node. If you want to change this, you have to specify explicitly input and output schema directly. Okay, quite understood. This is useful when you have a lot of keys more explicitly for input outputs. Okay, so in input you want to pass different kind of things, right? In input and in output you want like yes or no. Simple. So we will come to that as well. How to use guide and everything. Let's see there. Matlab, if you have a time, let why not go there. Okay, we can't understand this logic here. Let's move on there. Multiple schemas. Typically, all nodes communicate with a single schema. Okay, so we till now understood that all nodes have the schema, and I have the thinking that every node have a same schema. But what they have written key multiple schemas means multiple nodes have a multiple schemas. Typically, all growth nodes communicate with a single schema. This means that they will read and write to same state channel, but there are cases there will be more sorry control over this. Internal nodes can pass information that is not requiring graphs input and output. We may also want to use different input output schemas for the graph. Okay, so they have created scenarios where the state of the graph will be different. Like what I told you, right? Uh, in different cases, it may be different. different. It's possible to have a nodes write to private state channel inside a graph for internal nodes communication. Matlab, there's a subgraph there, they have some kind of communication going on that passes yes or no to the main chain, and based on that they do some processing and regular communication, right? Main chain. It's also possible. Sorry, it is possible to have a node's private state in graph internal communication. We can simply define private schema, private state. So what they have done, they have defined everything, every object already for you. I'm not sure we will be using this regress kind of a thing. I'm not sure I will be able to use that, the private state and everything. I like to keep things very simple. It is possible to define explicit input output schemas for the graph. Okay, in this case, we define internal schema to contain all keys relevant to graph operations, but we also define input and output schemas. They are subset of internal schemas to constrain the input output of the graph. See this guide for more detail. We'll come to see that. Okay, so there is an input state variable. This is a class output state variable. There is an overall state. Okay, so we have a user input, or this is the overall state. Okay, and this is a private state. So what they have done, they have built a sample graph. Node one state input state. It's from there we get the overall state. So we get the foo, and the foo we have a state input plus name. Okay, state 2 takes the overall state and gives to private state, and its private state to output state. Write to overall state, so it writes to overall state. Read from overall state and write to private state. It's quite understood. ठीक है, state graph, in state graph what we got is overall state in okay, input schema is input state, output schema is output state. Okay, so they have defined some schema, output state, input state, and something like that. Okay, so we have added one, two, three nodes, node one, node two, node three. We have add edges from start to node one. Okay, guys. Start to node one to node two, node two to node three to end. So this is sequential kind of a chain. Builder to compile user dot input my, and graph output is my name is lens. Okay, it's good. There are two subtle and important points to note here. We pass state input state as input schema to node 1, but we write it out foo and channel in overall state, a channel in overall state. How can we write out a state channel that is not included in input? So this is because a node can write to any state channel in graph state. The graph state is the union of the state channels defined at utilization, which includes overall state, all filters, state, output state. Okay. Um, we pass the state input as a schema to node 1. So node 1 we input state, right? And we pass it to overall state. So it is saying in input schema, this is because a node can write to any state graph. A node, any kind of a node can write state to any kind of schema. Okay. The graph state is a union of the state of the graph. Okay. The graph state is the union of all the schemas. Okay. So graph state contains everything schema and schema and everything what is present in all the node schemas. You, so how can we write to private state in node 2? How does the graph gain access to the schema if not passed into state graph initialization? Okay, so why it is able to write a private node right from here? So we can do this because nodes can declare additional state channels as long as the state schema definition exists. So I think additional schema can be added. Well, will compile. When they compile the graph, they see ki, okay, this is the extra thing we can add internally to that. So in node 2, private is already added. E, okay. Reducers. Okay. Now we have learned till now. We have got like good idea. Reducers are key to understand how updates from node to applied to state. Oh, how updates from nodes are applied to state. So, mm, so from wrapper to internal state, right? From node to state, how it is applied. Each key in a state has its own independent reducer function. Each key in a state. So state is built of like type dictionary, something kind of a variable, like it's different. They have a different reducers. Okay, and reducer function is explicitly defined when it assumes that updates to that key should override it. Okay, there are few different types of reducers, starting with default type of reducers. There are two examples how to use default reducers from extension class state listener. In this example, no reducer function is specified for any key. Yeah, that is clearly understood. Just they have defined the state of the variable key, how the state of the variable will look, node will look like. Right. Let's assume the input to the graph is foo1 bar is high. Okay, cool. Let's then assume that the first node returns foo2. Okay, we enter the foo1 bar h1 and we get the foo2. Okay, and then it is treated as an update to the state. Notice that node does not need to return the whole state schema, just an update. After applying this update, the state would be foo2 bar high. If the second node returns bar by, then the state would be foo2 bar by. Okay, 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 okay. Now let's see. In a state, in from a starting node, we pass this foo bar one, right? In node 2, now the first node returns foo2. It will return foo2. Then the notice that the node does not need to return the whole state schema, right? So it is returning foo2. After applying this update, the state should be foo2. The state variable will be changed, right? And it will be applied foo2 bar high. It will take this one and apply, okay, foo is 2. Okay, if the second node returns, then the return state would be foo2 bar by. Okay, okay, okay. Now, example B. In this example, we have used the annotated type of a specified reducer function. Last time we used simply list and everything, right? So what it's saying in previous example, it's just overwriting the variables. Let's say foo becomes 1 to 2, so it creates the state of foo to 2 in the next node. So state is going to be changed, something like that. So it's continuously changing. Notice that the first key argument remains unchanged. Let's assume that the input graph of the graph is foo1 bar high. Then let's assume the next node returns foo2. Okay, next node return, node 1 gets this. The first node returns foo2. Foo2 return node from node 1, we got the foo2. This input was that, output was this. This is treated as an update to the state. Okay, notice that the node does not need to return the whole state of the schema, just an update. Yeah, we understood that part. We know. After applying this update, the state would be foo2 bar high. If the second node isn't by, then the state would be foo2. Okay, okay. When used annotated, it is appending based on this. So we are saying annotate that. And annotation, you add those variables. Notice that there is a bar key everywhere working with. So okay, now we got the little bit understanding how it is working. Working with messages in a graph state. Why use messages? Most modern LLM providers have a chat model interface that accept. We already know that is chat model in this state. Input language chat model is a particular accepts list of message inputs as an input. These come in a long variety, just as such as human is a user input. So we got to know how to have a user input based on human message or AI message. So it's assistant, user assistant. With instead of that, they have created a particular function. You don't need to clearly define it in a JSON kind of a format. You just pass it on human message and AI message kind of a thing. To read more objects, this conceptual guide. We will come to that. We are very noise in this kind of a thing. Using messages in your graph. Okay. Okay. In many cases, it is helpful to store prior conversation history as a list of messages in your graph state. Okay. In your state, it is helpful to store prior conversation history as a list of messages in your graph state. Mm, yeah, that is true. To do so, we can add a key channel to the graph state that stores a list of message objects that annotate it and reducer function. See message key in example below. A reducer function is a vital to telling graph that how to update a list of message objects in a state. Each state updates. For example, when node sends an update, if you don't specify reducer, every state will overwrite the list of messages by the most recent value. If you want to simply append the message to the existing list, you have to use the operator or well, whatever that they are saying ki traditionally, like if you have used OpenAI, append the messages that they are coming, so it creates a conversation history kind of a thing. If you're not doing that, it's going. Okay, guys, so let's start again. Okay, so we were define input output schema. Okay. Mm, let's not go there. Let's come here. Okay, if you want to simply append the message to the existing list, use the operator. We exactly saw see that. However, you want to manually update the message in your graph state using if you were to operate it manually existing message instead of using updating existing message. To avoid that, you need a reducer that can track the message IDs, override the existing message. If updated to achieve this, you need the pre-built add message function. For a brand new message, it will simply append an existing. What it's saying ki for duplicate message, it's going to remain there. Let's say there's some kind of a loop you have created, right? A state variable will be changing under every point of the time. So the add message kind of a functionality, when that some message is not required, is going to override, and if it is required, it will append the message into the state variable. Something like that. Serialization. Okay. In addition to keeping message of a message IDs in add message function, we will try to deserialize message into LangChain message. Okay. Whenever a state update is received on the message channel, see more LangChain serialization here. The allow means graph input state into format. This is supported. This is also supported. Okay, I told you human message, AI message, something kind of that. Since the state updates always deserialize into lang chain messages when using add message, you should use the dot notation to access the messages like state message minus content. Below is an example of state that uses add message as a reducer function. Okay. Hmm. ठीक है मतलब it, like add message add messages is it's kind of a loose add only with these steroids, right? And what you're how you're going to access is like state messages minus one content messages state. Okay, since having a list of messages in your state room is common, that's quite understood. There is a pre-built state called message state, which makes it easy to use messages. Message state is defined with a single message key, is list of any message objects. So they have created the messages library, which has a messages state, and message is defined with a single messages. So it has built with the single key in a single message state, like in a base state. How they have a state has um, state created, and under that we have now messages. So in message is runtime kind of a base state kind of object only, which is a message state. Nodes in LangGraph, nodes are Python function, either synchronous or asynchronous, that accept the following state. The state of the graph we already seen. The config, a runnable config that contains a configuration information like thread ID, tracing information like tags. Okay. uh Okay, till now we knew nodes has only state, but now I have a three things: config, state, config, and runtime. Runnable config that contains configuration information like thread ID. So in what thread is going to run? Runtime objects that contains runtime context and other information like stored and stream writer. Similar to network guys, you can add these nodes to a graph using add node method. Okay, they have built something over network X. Okay, so LangChain data classes from data class type dictionary. They are importing for the state enable configuration for state graph for the having a state of the state. They have type dictionary for data class. They have imported context. Just a second. Okay, guys. ठीक है. So in context, we got the user ID string, and so we have a builder. So state graph is going to help us to create a state of the graph. Okay, so we have defined the state graph, and we have defined the state. State is nothing but what is going to be stored in our state variables. Okay, then we have a plain node. So now we are going to now we have defined the state. Now after that we are going to see what is going to be stored in a node. ठीक है. Now we go to plain node, right? And the plain, so then we are going to see key it's taking a state variable, and okay, so it's taking a state variable and it's returning a state. Okay, node with runtime. I'm not sure what is a node with a runtime is. Okay, ठीक है, let's see. It's taking a state. Okay, it's going to take a state, and what is it going? Okay, runtime is nothing but this object only. Object that contains runtime context. Other information like store and stream writer. Okay, it's going to help us to write things on the real time in our objects. Maybe we will come into that part as well. So it's going to print in note the runtime context dot user ID. Okay, it returns something like that. So one thing to note is that it's not taking the schema of the state. It's not taking a state variable, as in it's defining its own schema. So from that we exactly know the state is not going to be consistent, and the overall state of the graph will remain the union of the states of the input output schema of the nodes. The node with the config. Okay, so there is another node with a config. So we have a node with configs as well. So in this node, the thread ID is something like that. Hello state input. Oh, we are using the state here. So state is going to help us. Okay, the state contains your data, and how you are going to pass into the next thing. It's going to it's going to be defined by the node function. How's the nodes are defined. Behind the scene, functions are converted to runnable lambdas. The functions are converted to runnable lambdas, which add batch and async support to a function, and which add native tracing. So it's nothing but a uh, mm, wrapper over that function. See? So so what Langsmith is going to do? It's going to use that. So it's nothing loggers or everything has been contained there. So maybe they will be using these runnable lambdas inbuilt, and with the help of that they are going to get the context and everything uh, in the dashboard that professionally they use. If you add a node to a graph without specifying name, it will be given a default name equivalent to function name. So that is very clearly known. Okay, start node. The start node is special node that represents a node that sends the user input. Okay, node is special node that represents the node that sends the user input to the graph. Let me see. Represent node that sends the user input to graph. Okay, well, this is a sample node that they created, like start node and end node that I told you. Nothing else. And node caching. We support caching of nodes based on input output. To use the caching, specify cache when computer compiling a graph. Specifying a cache policy for node is each cache policy supports key function used to generate a cache key based on input, which defaults to a hash. So cache key is used to hash the data of the whatever that state is present. TTL, the time to live of the cache. Yeah, it's quite understood. We don't want to have a data present to till infinity. Okay, let's see the state graph. The example here. We have defined the state, we have defined the how is going, what is the overall state going to look like of the graph. Expensive node, okay, time dot sleep written, okay. Bill dot expensive node, there they get cache policy ttl3, okay. So t plus 2, so for 2 seconds it's going to sleep and 3 seconds is going to maintain the, yep. Graph dot invoke stream dot mode dot updates, ठीक है. तो x equals to 5, so it will be sleep for 2 seconds at to 10, ठीक है. Okay, so it takes 2 seconds and it takes only returns quickly because ttl is 3. So when we run this flow, the time was slow, so it takes 2 seconds to return this variable. And when we again run that within the time frame of ttl, it ran quickly. Okay, edges define. Now come to edges. Edges define how the logic is routed and how the graph decides to stop. This is a big part of your agent work and how different nodes communicate with each other. There are few types of edges. Normal edges, conditional edges, entry point, and conditional entry point. Okay, this is very important actually. Let me mark it down somewhere. Serialization we have already discussed. Nodes we have already discussed. Node caching we have already discussed. So let me mark this very important. How we are going to mark this? Let's highlight this. ठीक है. Normal edges, we go directly from one node to next node. Condition call a function to determine which node to go to next. Okay. Let's say I go from, okay, kind of a router. Entry point, which is user input arrives. Conditional entry point, call a function to determine which nodes to call first when a user input arrives. Okay. So we can have a multiple inputs as well. Based on that, what I understood, node can have a multiple outgoing edges. If a node has multiple outgoing edges, all of this distribution node will be executed in a parallel as a part of a next super step. Super step we have already discussed this part. Normal edges, if you always want to go from node A to node B, you can always, ठीक है, I think that is understood. If you want to optionally go from node 1 to more edges, you can use the add conditional method. This method accepts the name of a node and routing methods to call. ठीक है. Similar to routing function accepts the current state of the graph and returns a value. By default, a value returning routing function is used as the name of the node. Okay. So routing function returns the name of the node that it wants to go. ठीक है. ठीक है. That make sense. Okay. Okay, we can also identify, let's say, routing function returns true or false. So basically, we can define node B, node C. That is good. Entry point. Okay, start node A. Conditional entry point. Okay, ठीक है. By default, nodes and edges are defined ahead of time, operate on the same shared state. However, there can be cases where the exact edges are not known ahead of time and you will want to different versions of a state to exist at the same time. A common example of this is the map reduced design of a CAD pattern. In this design pattern, the first node may be a general list of objects. You may want to apply some node to all of the objects, like some other nodes. The no number of objects may be known ahead of a time, meaning a number of edges may be not be known, and the input state to downstream node could be different. Okay, to support this design pattern, Lang graph supports returning send objects from conditional edges and takes two arguments. First is the second first name of the node, second is second state to pass on. ठीक है. We want to send it to generate jokes if the subject of S is S in subjects. Okay. Okay. We want to send it again and again and again. Okay, we want to boot updates, perform updates. Acha, command. So command is going to help us the update and move it to next state. Okay, it's kind of having the annotated wala thing, but without having add operator added to it. So what it is, it updates the variable in the present in the state. Okay, so command literal mother node. With command, you can also achieve dynamic control flow behavior identical to conditional edges. ठीक है. So if want to state have a state equals to foo bar. So okay, so we can have a if else kind of a structure as well with the help of a command. And okay, so I think these two terms are very closely related. So command is basically to update the state, but conditional doesn't update that our state object. So we need to update the graph state and route to different node. For example, while implementing a multi-agent handoffs. Okay, so when from one place you wanted to move two different areas, you don't want to have a state going here and here to be seen, because otherwise both of these agents will be nodes will be performing same kind of a thing on the same kind of object, right? So in, let's say this is a kind of a scenario. Let's say there's a possibility a number can be one or two, but let's say between one or four. So there's a possibility two or three only, right? So you want to send two here, three here, so they can be computed parallelly, right? So this kind of a thing. So you don't want to send two here, right? Three here again. And so that's where the state update functionality will come into play. But it's important to route a different agent, pass on to different agent. Use conditional edges to route between conditional without updating. So yeah, conditionally we have only one thing. There is no going to be update in the state. Okay, we can move to another subgraph as well. Command dot parent and command. When you spend graph migration. In LangGraph, you can easily handle migration of graph nodes. For threads of the end of the graph, you interrupted topology prioritize the solution. For modifying state, we will back movewards. So let's come to runtime context and recursion limits. Okay, we are close to this completion. Let's come to runtime context. When creating a graph, you can specify a context schema for runtime context passed to nodes. It is useful for passing information to nodes that is not the part of the graph state. For example, you might want to pass dependencies as model and database connection. Okay. Okay. String is equals to OpenAI context schema. ठीक है. And you wanted to pass on this. ठीक है. In runtime context, it is very useful. So what we can do, we can create a data class separately, where we are fetching a data from some DB where we have stored our URLs and everything kind of a things. From there, we are calling the context schema here, so it provides the encapsulation property. So it's all loose, right? So it's quite understood when you're using these kind of concepts. And pass this context into graphing context variable to invoke method. Okay, and provide. Yeah, I think that's cool. We can also have a recursion limit. Okay, yeah. Now I think we are good to go. We got the idea, right? What we got the idea. Let's revise one thing. What we learned today. We learned what is the graph. Graph. Why lang graph is using graph. Graph contains three things: start, state, node, and edges, right? And there's a state graph. which has the state object, state thing, which has the state thing, right? And why we compile, what is a schema, what is a multi schema, what is the reducers, we going to know what is the why best, how the serialization work, how the message state is node, what is the node contains state config runtime, right? We see how these things work, what is the start node, end node, node caching, we see the edges, we see the normal edges, we see the conditional edges, we see the entry point, conditional entry point, we see the send command, uh, and we see the navigating into the parent node, we see the how navigating the subgraphs works, we see the migrations work, what is the runtime context, how is going to help us in the production environment, right? What is the recursion limit? So when there's a graph, you always, whenever you working something which has a cycle, you always wanted to limit something somewhere, right? So this is a recursion limit. So I think they have explicitly set to 25 steps, means yeah, 25 steps. So it's not going to seek, okay, more than 25 nodes in a one way, it's not going to traverse more than that. So you have to set explicitly, okay, more than that you don't go there. Okay, so I think today we got the little bit of idea. uh, let's go with the one example and we can wrap today. Let's see. So this is the simplest graph that um, the author in the course also explained. Let's build three nodes in a conditional edge. So we are going to build this kind of a graph, lang graph here. So let's do one thing. Let's pip install this. I like collabs because it's little messy, right? And for the presentation purposes, work very clearly and everything. And they've already shown uh, pre-built environments are created, so it's very fun to use those and very fast as well. So let's define the state. Yeah, let's see. We already know what is the state. Further, define the state. The state schema as the server input for node and edges. We already know that. So they are using type dictionary. So we already know we can use type dictionary or Pydantic object. Right? So they are using type dictionary. In type dictionary can use graph state. So this is a string. So it only contains a string variable. Let's nodes. So nodes are just for the Python function. The first positional argument is the state as defined as above. So we already see nodes contain the states and edges also. And because the state is a type dictionary, the schema is defined above. Each node is access has can access the key graph state and with the state graph. So there is a state object. In state object, we already know in a type dictionary we have an object called graph state, so we can access that. So each graph can access that. Each node returns the value graph state. We already know a node returns input and output is a graph state, matlab, state only, because it is going to be fetched from one node to another node, and it's going to be feed into the edge or maybe to the next node. Each node returns a value of the graph state. By default, the new value returned to each node will override the prior state value. We already know that by default it works like that only because we are not having explicitly like annotated add or add messages. So it's going to override the graph state variable in the state. So graph state. So in node one, the schema is like we have imported a state. We already know node first argument is always going to be state, right? So in the graph state, so what we have written, it will return a graph state graph state plus IM, and the node 2 return graph state but happy, and node 3 will return graph state is I'm sad. Okay. Edges connect the nodes. Normal edges are used if you always go from one node to node 2, and conditional edges are used in optionally root nodes. Conditional edges are implemented. Okay, wait a second. Conditional edges are implemented as a function to return the next node. So conditional edge is nothing but a function which return different nodes in a if else, something like that, right? Let's import random typing literal. Okay, so I'm getting an idea what is going to print. Okay, let's see. Import random. So what they have done, they have created a function. Randomly it decides ki which function to call. It's kind of a LLM. It's hallucinate. Decide mode. Decide. So it's nothing but we are defining a node three. So just to tell you that this is the not a node three. This is going to define um, mm, 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 the which node to go, either node two or node three, right? So we already seen literal. It will return a literal node two or node three. Literal is nothing but we use in the Python as well, right? The user. So what we have got, the user input state variable. So we already know we got the state graph state variable. So it's so input is a state is nothing getting of the previous node, right? So we are raising that user input state graph state. Here what we have there, 50-50 chance. So random not random is nothing but have a 50-50 chance is either going to return 0.50 to previous that and 0.50 to front of that, because it always return value between 0 equals to greater than less than 1, something like that, right? Okay, now graph construction. We build the graph from our components defined above. Okay, now we got the state. So for graph we need three things: state, nodes, and edges, right? So we have all these three things. Now we are going to compile our graph and we are going to query it. The state graph class is the graph class that we can use. We can initialize the state graph with the state we have defined above, that we have added our edges, add our node and edges. Okay. Uh, have we added edges? Yeah, we have added edges. No, we have not added edges. We use the start node as a special node that's indicate this. The end node is a special node, is a terminal node. We have already know. We can visualize the graph as a mermaid diagram as well. Okay. Let's run this. So let's before jumping into the what's going to be input, let's see what we have. From Python 1 display, image and display, let's say it's going to represent the image only. From LangGraph, we are reading state graph start and end. From builder state graph, we are so we are creating a uh, uh, graph. This is a state graph. We have the variable state. This that's going to contain a state of the graph. Builder dot add node. We added three nodes: node one, node two, node three. And why it is showing error on node 1 is not defined. Okay, let's go there, and we have not run this. We have also not run this. Yes. Okay, now we have added the builder dot edges. Now we have added nodes. Now we want to add edges, right? From start to node 1. So we have set the entry point. The start was our entry point, node 1 is there. So now we have added, after node 1 we have added the conditional edge. See this graph, after node we want a conditional edge from node 2 to node 3, then to end. Okay. And this is how node 1 to decide mode. So decide mode is nothing but is going to define which it returns key which node name it's going to go there, right? Either it's going to node 2 or node 3. So it is going to there, and we have added node 2 to end, node 3 to end, and we are going to compile it. Let's run it. Yeah, something like this it will look like. Let's invoke the model. The compile graph implements the runnable protocol. Okay, we already know runnable protocol is needed to run this. This provides a standard way to execute a langchain components. Invoke is one of the methods used in an interface. The input dictionary graph state hi, this is lines which is set the initial value of the state dictionary. When invoke is called, the graph starts execution from start node. The in the progresses through the each node 1, node 3, node 2, node 3 in order, the conditional edge will traverse from node 1 to node 2 or 3 with use a 50-50 decision rule. That conditional edge. Each node each node function receives the current state and returns a new value. Okay, they will get a state from previous node, and for the first node it will return from a user, and which overrides the graph state. So graph has a particular state contained, right? And which will be held, which will help us We already know LangChain main component is nothing but handling a graph state. The execution continues until it reaches the end node. Now we are invoking graph one, graph state. Hi, this is lens. So it goes to node one, then it goes to node two. Now let's see. The first our node had the node one. So first is the graph state. Hi, we pass the hi. This is lens, and it says I am happy. So it goes from node one to node two, then end. Right. Let's rerun it and let's see. Okay, it's getting. Oh, okay, one time we get the set. Okay, now we got the set. Let's try to tweak it. Let's try to find it out. Let's try to tweak little bit here and there. And how we are going to do it is, hmm, how we are going to do it. Let's see. Let's print the graph state at every. Let's see. We added f here. Okay. Now we are going to see, and okay, let's build the graph as well. And now we are going to see how each node, how the state of the graph is being changed at every point of time. See, at node 1 it was high, this is lens, and node 2 it was high, this is lens. I am sorry. Yeah. Okay, let's wait a second. I think I have added one thing here, node 2 and node 3. Now I'll see that. Oh, still okay. We have not run this now. Okay, let's invoke this. On node 1, it was hi, this is lens. Node 2, it becomes node 2, hi, this is lens. I am, and the end it becomes I am happy. So, how the graph state is being changed. So, this is how the lang graph state graph is work. Now, how this state is being maintained. Let's let let's try to see I am sad as well. No? Yeah, see. So this is how. So this is how node 3 got the value, and this is how the node 3 outputted it. So we in this we got to see what is a lang graph, how it maintains different kind of a things, right? How it maintains its state. Why lang graph, lang chains is so good because it maintains the state. So today for this it's enough for today, and we'll start every weekend this kind of streams where we will learn simultaneously how to do how does LangChain works, how things move, right, and how LLM works and how different technologies work. So this is first of the ad stream.